Okay, if we have x minus 5 equals 0, how would you solve that one? Okay, and would the answer be just x equals 5? That's good. I did pick up 2 duplicates, so I apologize. I have 2 of the exact same up here. I'm not going to put them both up here. How about this one? How would we solve x cubed equals 125? In a cube root. And what would we get for our answer? What would we do to solve this? Can you write on your paper yes or no? Okay. If we were to square root both sides, you would have to assume plus or minus. Losing things. So I would get x equals plus or minus 5. Is that the exact same thing as x equals 5? No. Right, we would, but that's, I mean, what are we really doing here? I'm just manipulating things, and I want to show you that sometimes when you do stuff to both sides, however, it's totally exactly fine what this person did, and more than one person did. Sometimes when you manipulate the equations, you end up getting an extra solution or two. Does anybody remember what those are called? Extraneous. I'm going to write this down, and I'll hand everybody's paper back that I grabbed so you can write this stuff down as well. Sometimes when you manipulate the equation yourself, you might end up with an extraneous solution. All right, who was the other person that I grabbed that had x squared equals 25? Nah, who was the cube? Is there somebody else's paper I grabbed I didn't pick up besides this paper? Okay, so we're going to be doing things with trigonometric equations, and it's very possible that you might end up with extraneous solutions. How would you know that you ended up with an extraneous solution? Because you don't know what the original solution was. How would you know that there was an extraneous solution? If you get some answers, how do you know that they all work? How would you check your answers? You can plug them in. Or you can look at the graph. Okay? We just need to make sure that all of our answers work. All right? So, the first example. Oh, and by the way, we're still doing section 5.3, and tomorrow we're still going to do section 5.3. What we're doing with this section 5.3 is I've broken up into many different days, and we're doing just one kind out of one day. Like last week on block day, it was just solving by factoring. Now what we're going to do is we're going to solve by substitution, and there still might be factoring involved, but what you're going to see me do today is we're going to solve by substitution. That's right up here, solve by substitution. So it says in the directions, rewrite as a single trigonometric function. What I mean by that is when you look at 9 minus 12 sine x equals 4 cosine squared x, I have a sine over here and I have a cosine over here. I want to rewrite this somehow so it's all sines, or that it's all cosines, or that it's all tangents, like just so it's the same trigonometric ratio through the entire equation. That's what we're going to do today. So when you first look at this, oh, I know what else you need to take out, unless you have them memorized. Those 9 trigonometric Pythagorean identities. You got them memorized? Yeah, if you don't have those memorized, having those handy about now would be good. If you misplace them, they are available on the internet. Have to do. And some of you have the computers out because you're using Desmos, so it's fine. So we either need to take sine x out and change it sine x. Or we need to take cosine squared out and change it into sine. Or somehow make them all into tangent or something. But I think it's easy to just make one into the other. I think that's what the easiest thing is. So you're looking at your identities. Is sine x somehow equal to cosine x using those identities? How?
But it's 1 minus sine squared.
So let me ask the same question I just asked. Can I take sine x out and substitute it for something that has cosine x in it? No, because it's not squared. But cosine squared. So Jasmine, what were you going to say, huh?
You could change cosine squared x. 1 minus.
Right, so we're going to substitute. We have 9 minus 12 sine x equals 4 parentheses 1 minus sine squared x. And then I just distributed to get rid of those parentheses. So once you have all sines, now we should be able to solve this using something that we already went over so far in this class, which either we can just solve for sine x, or we might need to do some factoring to solve. When you look and you see we have a sine x, and over here we have sine squared x, what method do you think I'm going to need? I'm going to need factoring. So what should we do to both sides so we can factor? So I'm not allowed to factor right here. I have to make it say equal 0. Which side should I make 0? This one? Yeah. I would really like to factor with the squared term being a positive. You're more than welcome to make it negative, but I put it here, but they're not like terms. So once you have 4 sine squared x minus 12 sine x plus 5 equal to 0, we're going to factor it, and this is where people have trouble looking at it and kind of figuring out how to factor it, so you're more than welcome to take out sine x and make it like a u. Oops. And if that helps you to figure out how to factor it quicker, go for it. Either way, though, we're going to have minus minus. We're going to have one of them as a minus 1, one as a minus 5. And then it ends up being 2 sine x and 2 sine x by the time you factor it correctly. If you need help with factoring, you got to come in and see me. So then once you have it factored, what do we do to each factor? We're going to set it equal to 0, so we have 2 sine x minus 1 equals 0, and 2 sine x minus 5 equals 0. So I have sine x equals a half and sine x equals 5 halves. So the first one, sine x equals a half. Where is that going to happen? Well, 30 degrees is correct, but we're, according to the directions, we're finding radians. And also 5 pi over 6, because there's more than one answer. These are both positive. First and second quadrant. What? And then the second question, sine x equals 5 halves. It's not extraneous, but when you say undefined, it doesn't work. Like, it's never, ever 5 halves. So an extraneous solution would be one that does work here. You get an answer for, like you get a pi over something, and then you plug it back in, and it isn't true when you plug it back in. That's an extraneous solution. This is just like no solution, or undefined. So we just have 2 solutions. Let's go to Desmos, and let's check to make sure we did this right. There's 2 different ways you can plug it in. I want you to plug it in and check to see if it's right. There's two different ways you can plug this in. You're going to have to do it on your own, so choose which way you remember, and then we'll go over both. So don't put, oh yeah, don't put the E. It doesn't matter if you do it that way, but what we did in class, we didn't have them equal to each other. We either did it as one, or we did it as two separate, rather than having them equal to each other. Because otherwise you're just getting straight lines. What is that? Oh, no. That, I don't know. It's the, go to the wrench and change your step to 5 or 6. I don't know if that's what it means.
You gotta put it on. Yeah. You can't have it. Look how it's up on the fourth. It's not equal, it's minus.
Okay, so your choices are what we did in class. Remember, we solved it like a system where we had two separate equations, and then we looked to see where they equaled each other, where they overlapped. That was one method of solving it, or just to check your answers. So that was one method. The other method, if I just turn those off, the other method would be to set it equal to 0. And then where are we looking if it's set equal to 0? Yeah, we'll be looking at the x-intercepts, which again, exact same answer. So either method is fine. I didn't even type it in that way, so I don't even know. I have to play around with that. Because I typed it in, before changing. And you know what? I always want to type in the original equation. Because if you typed it into an equation somewhere down the line, you might be typing it in and it checks, but your equation that you're typing in might be the wrong equation. So I always try to type in the original equation before I did anything to it, before I manipulated it. So I could have made a mistake. All right, let's look at the next one. I want you to think for yourself. I'm going to have to switch out, and this is going to have to be all the same, exact same trig ratio. So look at 2 tangent squared x minus 3 secant x plus 3. What could we, you don't have to answer it out loud, I'm just talking. What could we switch out? Don't answer it out loud. Whenever I have a moment to think for that myself. Good. Have those identities out. Oh, you're back. Yeah, you want to switch up. Folks around the room, a lot of you figured it out. We're going to take out tangent squared x, and that is the same thing as secant squared x minus 1. So we're going to distribute. And then from here, I'm just going to collect my like terms. And once I've collected my like terms, we now have a trinomial. So if this is hard to look at and figure out how to factor, you could look at it being like 2u squared minus 3u plus 1. You're going to have to factor it. It's a trinomial. We're going to have a minus 1 and minus 1 for both of them. And then the first term is going to be like a 2 and a 1. So 2 secant x and 1 secant x. Then we set each equal to 0. We're going to solve each factor. So secant x equals a half. Cosine, change it into cosine. So where does cosine equal to? It never does. That's undefined. You can't use that piece of information. Secant x equals 1. You can change it into cosine. Where would cosine be equal to 1? So this says there's only one answer. Let's go on Desmos and check. Is 2 pi in the restriction in the directions? So that one won't work. Now remember, this is not the only way you can check it. You can check it by plugging it back into the original. But what I really like with Desmos is if there were more answers, I would see and know that I missed something. Plugging it back in to check the answers are only checking the ones you found. But if you didn't find some, you're not going to know some are missing unless you look at the graph. So from 0 to 2 pi, not including 2 pi, we only have one answer at x equals 0. Okay, go to the back. So we're looking at cosecant x and cotangent x, and we have to make them all the same. And when I first look at this, the first thing I think is that Pythagorean something? Why not? Okay, but aren't they together in one of those? They are together in one of those. So I wonder if there is a way to make one of those squares. So that example that we did at the beginning of class with x equals 5, how we had, oh, I squared both sides, that was common because of this one, but don't square both sides as is. Because if you do, it's going to be yucky. It's going to be yucky. So what I would suggest, if you are going to square both sides of any of these, you put one of those ratios on the other side before you start. So I'm going to do 1 minus cotangent x. It didn't matter which one you moved over, not at all. I'm going to move it over. Then I will square both sides. That way we only have cosecants on one side, and we only have cotangents on one side, rather than having them mixed. Because you are going to have to write this twice and FOIL it. So I've moved the cotangent over, then I squared both sides. I FOILed the 1 minus cotangent x, and was left over with a perfect square trinomial, 1 minus 2 cotangent x plus 2 plus cotangent squared x equals cosecant squared x. So now, using those Pythagorean identities, which one should I replace? Should I replace cosecant, or should I replace cotangent? Right, because if I replace cosecant, well, on the negative side, if I replace cotangent with like 1 minus cosecant or whatever it is, I'm going to still have a cotangent. But if I replace this one, what does it equal? Who's got it in front of them? Is it 1 plus?
Yeah.
1 plus cotangent squared? Now I'm going to have all cotangents. So we're manipulating this equation so that now we can solve it. And since we have a cotangent and we also have a cotangent squared, probably going to be by factoring. So I need to make it say equals 0. Which side should I make equal 0? Left side? So my 1 and my cotangent squared like both canceled out, and divide by -2 and I get cotangent x equals 0. So where is cotangent, which is x over y, equal to 0? So we are going to check this on Desmos, but I want to show you how to check it by hand just in case you don't have Desmos for something. So let's check this one by hand. Yes, sorry. You got it? So we're going to check this by hand. You want to check in the original equation, and there's 2 solutions. So we're going to check both of them. So I'm going to do cosecant of pi over 2 plus cotangent of pi over 2 equals 1. And then we're also going to do the same thing for 3 pi over 2. So we'll do cosecant of 3 pi over 2 plus cotangent of 3 pi over 2 equals 1. And you can use your calculator to check this, but I'm not going to because I don't know where mine is right now. Also, because it's easy. Cosecant of pi over 2, that is here. What's the answer? Cosecant, same thing as y. What's y? 1. Okay, and then cotangent is x over y. What's x over y here? Does that work?
Yes.
Okay. And what is cosecant at 3 pi over 2? So -1 and cotangent at 3 pi over 2. Does that one work? No. That is an extraneous solution. So our only answer is pi over 2. We can also graph it on Desmos, which I believe mine's already graphed if you just want to look at it real fast. You can also graph it on Desmos to check. Nope, mine's not. Nope. Nope, I lied. I thought mine was graphed. Guess not. What was it? Cosecant x plus cotangent x. It's not right. What did I type in wrong? Oh, -1, thank you. Or I could put equals 1, right? I mean, I could put the next one as 1. Anyway, here we are. Pi over 2. Only answer. All right, can you guys try? What time is it? Wait, what time are we at? Okay. Let's go to the last one. I'm gonna start handing out the worksheet just so I'm not like handing out as the bell rings, but I want you to try this one. And then I'm gonna jump in there and help you as well. The last one. Okay, what do you notice about one. Kind of different than the other. Yeah, 6 questions. Okay, so what do you notice about this is, are we going to be using the Pythagorean identities for this one? No. But there is a different identity that makes these the same. Not Pythagorean, but the reciprocal identities, kind of. Reciprocal identities. If I change cosecant into what? 1 over sine, we are kind of the same trigonometric ratio at this point. Huh? Oh gosh, you know what? I was like, oh no, you can't. Well, you can. You can add these. You can add fractions. How do you add fractions? Okay, so I can multiply this one by sine x over sine x, multiply by a value of 1. Makes the denominator the same as that one, so now we have 2 sine squared x over sine x plus 1 over sine x. Now I can add them together over the common denominator. So sure, you can add them. We're going to solve though. What do you think we could do to solve? Could multiply both sides by sine x. One way you could think about that is I'm cross multiplying. Or you could just multiply both sides by sine x over 1, because that's how you cancel out fractions. Either way, I think most people understand the cross multiplication more because you're used to it, but either method is totally fine. So if I cross multiply, then I'm going to get 2 sine squared x plus 1 equals 0. Which gets rid of that sine x term. Which means I don't have to do this by factoring. I can just solve it now. So we subtract 1 from both sides. Divide by 2. Square root. Then I get that sine x equals plus minus square root of negative 1/2. And Julie's making that face. Why are you making that face? Okay. So where, if you think back to the graph, if we were looking at this on the graph, where it equals 0, what are we looking at on the graph? What part of the graph would we be looking for the solutions? Right, that would be like the x-intercepts, because we're looking at where y equals 0, where it crosses. We'd be looking at the x-intercepts. What does it mean if it's imaginary? It means it doesn't cross the x-axis. So what's our answer? There's no solution. Let's check and make sure, though. I do have it graphed. I do have it graphed already. I know I have this one. I saw it earlier. Here it is. Does it cross the x-axis? No solution. It's important to use the checking method to validate that you're doing it right. Okay, your worksheet is only 6 questions. You can spend some time manipulating those equations and try to figure it out. Use Desmond as a tool to validate you're doing it right, or find out that you did it wrong and go back and fix your work. Don't just write down the answer sheet with Desmond, because you won't have that all the way.